Here's a quote from George Orwell in a famous essay on politics and the English language. A man may take a drink because he feels himself to be a failure, and then fail all the more completely because he drinks. It is rather the same thing that is happening to the English language. It becomes ugly and inaccurate because our thoughts are foolish. But the slovenliness of our language makes it easier for us to have foolish thoughts. Global warming, I think, fits this in many respects. It's clearly, and has been since the beginning, about politics and power rather than science. In science, there's an attempt to clarify. In global warming, language is misused in order to confuse and mislead the public. The misuse of language extends to the use of models. For the advocates of policies allegedly addressing global warming, the role of models is not to predict, but rather to justify the claim that catastrophe is possible. As the advocates of global warming understand, proving something to be impossible is itself almost impossible. In a further abuse of language, the advocates attempt to rephrase issues as yes-no issues. So, for example, you frequently hear questions like this: does climate change, is CO2 a greenhouse gas? Does adding greenhouse gas cause warming? Can man's activities cause increases in greenhouse gases? These yes-no questions are meaningless. Crucial to scientific method are how much questions. And that is certainly the case for the above questions. One should not fall for the temptation of trying to make absolute answers. Indeed, for the 4 questions I've listed, I think most skeptics, including myself, would answer yes. To a certain extent, therefore, this issue cannot be discussed between opponents. The truth is, we are speaking different languages. That said, it should be recognized, as has been mentioned by previous speakers, that the basis for a climate that is highly sensitive to added greenhouse gases is solely the computer models. The relation of this sensitivity to catastrophe, moreover, does not even emerge from the models, but from the fervid imagination of climate activists. Okay, what are some of the questions that are relevant? First one, which several people have discussed, is what is the sensitivity of global mean temperature to increases in greenhouse gases? What, if any, connection is there between weather events and global mean temperature anomaly? Is our understanding of the greenhouse effect adequate? How relevant is the simplistic notion of global mean radiative imbalance driving global mean temperature to actual climate change? This is something that's rarely asked. Obviously, this is not going to all be covered in any detail in this lecture, but we can go through some of the physics, and hopefully it'll be some help. As always, I mean, this is I mention this often, this is a primitive field, and many of the issues here are issues where none of us have that great a grasp on. The business of the greenhouse effect and the role of greenhouse in the Earth's temperature, I heard earlier today questions about it and so on. I actually think it is fairly simple. I mean, you start out with a picture. Let's say you have no atmosphere, you have the sun, you have the Earth. The sun is radiating at about 6,000 degrees Kelvin, and the flux is decreasing as the square of the distance from the Earth. The cross-section of the Earth is just pi r Earth squared, and the Earth will be, without an atmosphere, emitting radiation as sigma T4 times its total area. And that'll balance the part that was intercepted from the sun. And if you calculate this equation, you actually get something very different from what people mention. You get 272 degrees. How come people argue that, this is only, what, 16 degrees less than 288? Why is it argued that it's much less? Well, all the arguments use a plausible value for the albedo, the reflection of light from the sun, from the Earth. The only thing odd about that is most of the albedo comes from clouds, so it assumes an atmosphere with clouds but no atmosphere. Okay, so that gives you the 33 degrees difference. Let's see. It's this difference here that one speaks of as at the heart of the greenhouse effect. And here another notion comes in, namely, since the atmosphere's temperature decreases with altitude, and we'll discuss this further, this gives rise to the notion of a characteristic emission level where the temperature would be on the order of 255 degrees. Okay, a couple of points to remember from this. If we emit the albedo due mostly to clouds, you'd only be 16 degrees colder than we are today. The other thing that's equally important, if one changes the solar output by about 2%, which is roughly equivalent to doubling CO2, then the temperature changes about 1 degree. And that is, crudely speaking, the no feedback expected response from a doubling of CO2. Okay, one problem with the greenhouse effect that seems to drive certain people crazy is that they believe the picture presented by Al Gore of the blanket and the back radiation and this and that and so on. And so you have a lot of people immediately going to their notebook and saying, this is impossible. I have disproven the greenhouse effect. The truth is that isn't what the models use. It isn't what people really think. It's part of the fact that you're making up a story rather than telling what's happening. It's also, one attempt, which is really weird in science. You'll notice a lot of people say, this is a well-established effect. It was known to Fourier, it was known to Tyndall, it was known to Arrhenius, et cetera, et cetera. They don't mention that all of these people did it wrong and not the way it's done today. The crucial thing you have to remember for the actual, quote, greenhouse effect, let's not worry about semantics, is that the lower atmosphere, roughly between the tropopause, which varies with latitude, and the surface, really for this purpose should be viewed as a turbulently mixed layer. The turbulence in the tropics is the cumulonimbus towers. And in mid-latitudes, there are what are called baroclinic eddies, the cyclone waves, that transport heat along such sloping surfaces. They pretty much establish the structure of the temperature. It is due to this dynamics that the temperature is decreasing with height to the tropopause. In the tropics, it follows something called the moist adiabat, but for our purposes, it's roughly a decrease of 6.5 degrees per kilometer, and that is communicated to mid-latitudes by these eddies. There are obvious discrepancies in the Arctic where you have the inversion. In any event, the emission temperature of the Earth, 255 degrees Kelvin, can now be seen as the temperature of a characteristic emission layer, roughly about 5 kilometers above the surface and well within this turbulent slab. Now, for those of you who do radiative transfer, this is about 1 optical depth, crudely speaking, into the atmosphere. This is a schematic picture. I don't mean it to be precise. To have an emission level, you need greenhouse gases. That is, say, gases that absorb and emit in the infrared. The main such gas is CO2, is water vapor, but CO2, methane, etc., all contribute. In the absence of clouds, which happen also to be extremely powerful absorbers and emitters in the infrared, the characteristic emission level, as I said, will be 1 optical depth measured from space downward. You know, there's no question again. The optical properties of these gases vary with frequency or wavelength. 5 to 6 kilometers is a kind of average. When you add greenhouse gases to the atmosphere, you reach a unit optical depth at a higher level than you did before. And according to the fact that the temperature is decreasing with height, you're going to now be emitting from a temperature that is colder than the original level. This means that your outgoing infrared radiative flux, don't worry about balancing, it'll certainly be reduced. And as a result, the troposphere, which is a dynamically mixed layer, pretty much must warm as a whole, including the surface, while preserving its lapse rate. That is the rough picture of how it works. This is just an illustration of that. So you start out, you know, with the atmosphere. This is 1 optical depth in. If you're in balance, you're never really in equilibrium, but let's say you start in equilibrium, then you'll have the net incoming solar radiation, the outgoing long-wave radiation. You add some greenhouse gas, tau equals 1 moves up. As a result, the outgoing long-wave radiation is less than this. And if you ask that the system return to some equilibrium, that would involve the whole system warming until this again equaled that. That's these 3 pictures. Radiative forcing, when the IPCC refers to it, refers to the imbalance in this panel B. The usual estimate from the IPCC is that a doubling of CO2 gives you about 3.5 watts per meter squared. I don't care if it's, you know, plus or minus a half. And as we saw before, that's about 2% of the incoming and outgoing values, and we changed the surface temperature about 1 degree centigrade. There's a problem with the characteristic emission level, which I should mention right off the bat. It's endemic. The infrared actually comes from a number of levels. The most obvious ones are the surface in the infrared window, the characteristic emission level for the gases, and then the infrared that emerges from the upper level cirrus clouds. The interesting thing is that both CO2 and clouds act to close the window for this. And where you have the clouds, these levels don't matter. That does change things a little bit, or more than a little bit, I should say. The upper level cirrus coverage is on the order of 35%. I mean, this is not negligible. These are very thin clouds. They're barely visible. Sometimes they're not visible. The typical altitude for these clouds is about 10 kilometers, where the temperature is about 223 degrees Kelvin. Once you consider this, the characteristic emission level away from these clouds is actually 268, which puts it much lower. There are a couple of things to note with the clouds. They also reflect shortwave radiation. This is something we mentioned, that the upper level cirrus often have substantial infrared opacity with little reflectivity. And when clouds are below the characteristic emission level for gases, they don't impact things much. It's only when they're above. Okay, calculations of radiative forcing to a doubling of CO2 tend to ignore the shielding effect of upper level cirrus clouds. This is worth noting. Let's for the moment consider that the radiative forcing we're talking about is 3 watts per meter squared. You know, the discussion, all the discussion we're having makes it sound as though we're talking about a big thing. We're talking about a little thing. We don't measure to this accuracy. Moreover, such small changes can be caused by many, many things. So, for example, when you're talking about upper level cirrus, which are very variable, a 10% change in their area or 500 meter change in altitude give you 3 watts per meter squared. And fluctuations of this magnitude and even larger are common. If the changes are caused by changes in surface temperature, they're feedbacks. But there are many things that can cause such changes. And as a result, most of them are not feedbacks. They're just noise in the system from this point of view. But they can all override this little change if you doubled CO2. I think ultimately, and I can't give you this at the moment, all these changes should be viewed as what I would call degrees of freedom, whereby a climate system can adjust to any sort of imbalance. In any event, let's continue with feedback. What does that mean? Well, we usually view the system as having a node. This is the system. It has a 0 feedback gain. You force it with certain radiative forcing, and you get out a temperature. And this is the 1 degree if this is the 3.5 watts per meter squared. If you have feedback, what it's saying is the change in delta T gives rise to a change in the flux in the system, so that the total flux is a response not just to the original delta Q, but also to this feedback factor. And if you solve for it, you get this, or more accurately is a relative issue, to the sum of all the feedback factors. The thing to notice about this is the expression for delta T is singular. If the sum of the feedback factors equals 1, you are getting infinite response. Of course, that's not real. We know that, simple resonance gives you infinite response, but there's always any little thing will prevent it from being infinite. Nevertheless, it's worth keeping in mind, because this is just another picture of how to view it. You have the incoming, you add greenhouse gas, and then you add something like water vapor or something, and you increase the imbalance in a positive feedback. But in the real climate system, you can also have negative feedbacks. Let's just skip this. This is an important curve to understand, because we'll come back to it a number of times. This is the response of the system in terms of the total feedback factor. And remember, I said it's singular, and it's the sum of the various feedback factors. So if you start out with, let's say, 0.5, anything you add to it gives you a huge increase in the response. But if you are in this area here, changes in the feedback factor do very little. This is the nature of a function 1 over 1 minus f. This is just the words that I've said. For positive feedbacks, small variations in the feedback lead to large changes in response. And for negative feedbacks, large variations in the feedback lead to only small changes in the response. Essentially, any degree of freedom that can provide 3 watts per meter squared is also large enough to provide feedback factors of plus or minus 1. That's why the range of uncertainty has remained so large over the years. In all current models, and this is important, there is something they call the water vapor feedback, which provides F equals 0.5. That is to say, it brings you to here. And as a result, any additional small feedbacks can lead to huge sensitivity. So for instance, with 0.5, it's 1 over 1 minus 0.5, gives you 2. That's fine. Then somebody adds 0.3 to that. That's even smaller than the water vapor feedback. You're suddenly at 5. If somebody were to add 0.5 again, you're infinite. So that's the issue in the uncertainty. There's another feature here that we'll focus on, and Near mentioned it. A sensitivity can also be expressed as a ratio at the surface of flux to temperature change, okay? A highly sensitive system has a very big delta T for a very small flux. That's also a measure of the coupling of the atmosphere and the ocean. If you have a very small flux, no matter how big the delta T, you're still going to, by the first law of thermodynamics, have to use that flux to reach that delta T, so it'll take longer and longer and longer the more sensitive you are. And there are a lot of issues with this. We'll mention some of them. But one of the things that suggests a problem with the field, you all probably have heard of things like the Pacific Decadal Oscillation, the Atlantic Multidecadal. These are names, don't take the names literally, but they represent the fact that in the Earth's climate, there are fluctuations on long time scales, ranging from 10 to 60 and even longer times, that involve the interaction of the atmosphere and the ocean. This is best worked out for El Nino, ENSO, but the others also have that characteristic. No model gets those things in a reasonable manner. And so I've suggested that since they all involve interactions of the atmosphere and the ocean, why not rig a model? You can make a model that will be less sensitive, artificially, and see if those models do better on the Pacific Decadal Oscillation or on ENSO or any of these things. I have yet to find a modeling group that will try that. So, you know, that's one of the unfortunate features. Now, in trying to assess the sensitivity, the natural thing to consider is that the temperature record itself should tell you something. This is not rigorously true, though I think the record is very suggestive. This figure you've seen already. Essentially, the IPCC, in arguing for attributing the warming that appears between about 1960 and 1997 to anthropogenic emissions, I should add, not greenhouse emissions, total emissions, including aerosols. We'll come back to that. Does not give you the observed warming. So they say, well, we're pretty sure that means since we can't think of anything else, it must be this. Everyone knows that's a stupid argument. And in particular, you know, all sorts of things could be this. You've heard people suggest it might be a solar effect. But there are plenty of variations on this level. We're talking about tenths of a degree, for crying out loud, that are always occurring. Indeed, if you plot the warming that was actually occurring, not the model results, between 1920 and 1940, it's indistinguishable from this. So their argument in the IPCC is that they need anthropogenic influences after 1960. You know, as we've said, this assumes that you knew exactly what was going on, and that's grossly unlikely. I'm going to look at this picture, and we'll see what went into it. There are the issues of volcanoes and so on. Let me show you what I want to do. Even the IPCC, I should mention, when they do scenarios, do not use the GCMs. For the most part, they use very simple ocean-atmosphere energy balance models because they have the time lag. They basically behave like the large models. So we'll use one such model. Here is the latest IPCC, you know, the radiative forcing. These numbers probably are invisible to you, but fundamentally, what is interesting to me is if you take the greenhouse gases, they are estimated with an interesting amount of uncertainty, even for CO2, to give you about 2.93 watts per meter squared. And then they say that the total anthropogenic radiative forcing, on average, is about 2.29. They get that by subtracting the aerosols. Now, you will notice that although there are error bars, if you look carefully, the impact of aerosols has come down in this IPCC, and so has the uncertainty for the primary aerosols. The secondary aerosol effect due to aerosols affecting clouds and so on is also considered to be small, but it has uncertainty. They list like this. They don't list this. This is in the text, and it's a nice example. The text says if you're dealing with ice clouds in the high troposphere, the effect can be the opposite sign. It can actually be to add to the warming rather than cooling. At any rate, let's take the total forcing. Remember, this is now 80-some-odd% of what you get from a doubling of CO2. So the whole discussion, you know, we're going to double CO2 by such and such a date, from the point of view of radiative forcing is largely irrelevant. We've reached it. And so let's see what, okay, total greenhouse forcing, crudely speaking, from 1800 to the present, looks like this for the total greenhouse forcing. E-folding is on the order of 40 to 60 years, reaches little under 3 watts per meter squared. Now, in addition to this, all the simple models use some measure of volcanic forcing. Most of the models use something developed by Sato at Goddard Institute for Space Studies. And you notice here, that's popping up, you know, to between 1 watt per meter squared and 4. It's interesting how volcanoes go. You have a cluster of volcanoes around Krakatoa in the late 19th century. Then have a period relatively free of major volcanoes. Then you have a cluster again. I don't give much significance to the clustering. You're all aware that a random process gives you clustering. The odds of getting things, if you're flipping a coin, head, tail, is 0. There will always be runs. And so this you have in addition. And we'll see what that does. Here's the simple model we use. You have the flux, you have the emission, and then you have an ocean consisting in a mixed layer where you have instant mixing, a thermocline with diffusion, and upwelling or a bottom to the thermocline. This is the model, type of model used in scenario building. The forcing at the surface, you have to be careful. It's not radiative forcing. The only thing one is saying is the divergence of flux is zero. We're not saying the divergence of radiative flux is zero. So at the surface, it's mostly what is called latent heating, flux of water vapor, also flux of sensible heat or other components. It's the total that we're concerned with. And keep in mind, high sensitivity, long response times. Okay, so here's the response to the volcanoes. Now, what's interesting about that is each of these curves represents a different sensitivity. So the lowest sensitivity is 0.75, used for a doubling of CO2. The highest is 5. That's the bottom curve here. The thing that's interesting about it is if you have low sensitivity, the volcanoes just appear as transient dips in temperature. If you look at the temperature record, you can't be certain, but you don't see anything other than dips in it. Whereas if you have a sensitive climate, it kind of says that there's a secular effect, that, you know, the response, the decay lasts longer and longer, and so it forms a platform for the next volcano and the next volcano. And so you're always building down. The interesting thing about it is if you have greater sensitivity than 3 degrees centigrade, the volcanoes give you a net cooling of about 1/3 of a degree already over the period you're looking at here. Okay, this is the response to just the greenhouse gases. And so essentially, you're seeing the range from 0.5 or so to about 2 point something for the 5 degrees centigrade. Now, of course, you're not seeing 5. You're only seeing half because it takes a long time. There is the delay due to the heat capacity of the simple ocean. Nevertheless, the actual change, if you assumed everything were due to the processes we've mentioned, is somewhere around here. So already these are much larger. If you add the greenhouse response to the volcanic response, you now reduce the difference between these because the volcanoes, for the high sensitivity, have also subtracted a great deal. But you're still way above what you expect here. Now, finally, all the models will end up agreeing with the observations. How do they do that? They do that by subtracting with aerosols, which they also call anthropogenic emissions, whatever they need to bring them into line. Well, with 0.75, you would need 0. Remember, we're accounting for all the temperature change by anthropogenic plus the volcanoes, which they include. By 1.5 degrees sensitivity, you already have to subtract 25% of 3. So you have around 0.7 watts per meter squared. Beyond this, you're having to subtract over half of 3. Remember, the IPCC best estimate for aerosols is 0.75. So essentially you're already getting to the point where you're pushing the limits of what people think aerosols can do. Bjorn Stevens at the Max Planck is currently suggesting, and the paper is in review, so he doesn't want to be overly certain about it. He's suggesting that it's terribly unlikely that aerosols currently provide more than a half watt per meter squared. And at that point, sensitivities in excess of 1.5 C are impossible unless natural internal variability is now used as the new fudge factor. You always have that. Remember what I said. For the people who are advocating global warming, the only thing they need is the possibility, not that they made a correct prediction. Okay. Now, the curious thing is, if you look at the data, there is no sign of the deep, prolonged response to volcanoes that would indicate high sensitivity. But there's a curious thing, and I won't stress it too much, but the Hadley Center does complain that in 2009, they still had a problem of the influence of Krakatoa from 1883. It wasn't strictly in temperature, but it's curious. Moreover, the thing we have discussed very little is natural internal variability. What I mean by that, and this is important, we're keeping on talking what controls the climate. This may be the wrong question. Climate will vary without any forcing at all. I hope you all understand that. You don't need the sun. You don't need increased greenhouse gases. You'll still get ENSO. You'll still get Pacific decadal oscillation. You'll still get Atlantic multi-decadal oscillations. And you'll still get ocean overturning due to the formation of deep water that can take 1,000 years or more. People attempted, Tung and Zhao, in a paper in the Proceedings of the National Academy of Sciences in 2013, to try and estimate how much of the warming was due to natural internal variability. And they came to the conclusion that it was at least half. If that is the case, then if one went back, you would have to subtract double this to get agreement, at which point you'd be out of the realm of possibility. In a normal world, where, in this one version or another of this graph has been shown already, here is what you get since 1975 from the tropospheric temperature changes. Here are all the IPCC models. They not only differ hugely from each other, admittedly over a small range, but they all practically are out of the range of the observations. At this meeting, but also a lot of other people, have made the point that with this spaghetti here, the model ensemble, to use the average of the model ensemble as the IPCC does, is absurd. If you were an engineer and you were confronted by this, even if you didn't understand the situation, you'd say, a few models are at least in range. How do they differ from all the other models? Let's throw away the other models and find out why they did so much worse. Instead, in the democratic processes of the UN, all models are equal. The reason I say you can't get sensitivity per se out of it is you have the fudge factors, and so you can always argue, however implausibly, that it's possible you have high sensitivity. you have to understand that in the normal world, for instance, with tobacco and lung cancer, all the studies had problems. What was leading to the conclusion that you were causing lung cancer was a meta-analysis combining all the studies and saying if they're all pointing in the same direction, one probably should give more statistical confidence to the result, even if the individual studies had problems. This is the situation one's in with the temperature changes itself. Normally they tell you your problems are all in one direction. It probably suggests lower sensitivity. Now, there are other ways of looking at it. Sensitivity. I'll go through a few of them. We mentioned time scale. Gerard Rowe in 2009 made a very simple point that the Pacific decadal oscillation, which has an index, really, this is a story, almost all the oceanographers like, but that the Pacific decadal oscillation is not decadal, it's not an oscillation, but at least it's in the Pacific. It behaves as a first-order Markov process with a certain response time. The interesting thing is the response time is about 1.6 years. And that would give you series that look like the Pacific decadal oscillation. There's a simple thing you can do, which the IPCC has this CMIP program at Lawrence Livermore. So you have all the model results. You can look at North Pacific temperatures, for instance, and ask if you try to model them with an autoregressive process, what is the response time you get from the model versus what you get for the data? And this is just why you can use temperature instead. But what you got for the models was almost all the models that had enough to do this were getting somewhere on the order of 25, 28 months. And the response time in the data is typically around the order of 10 to 15. Again, it suggests model sensitivity is excessive. It's not convincing. Obvious approach is to try and measure the feedbacks. And I've done this with a colleague, Young-Sung Choi, which is to use satellites to look at the outgoing long-wave radiation and compare that with what the models give you for the same sea surface temperature. It's a technical issue, and I won't spend a lot of time. I promised Wolfgang that I would not continue indefinitely. But let me just, it's available for you who want to. But the thing about it is, it leads to looking at long wave and short wave outgoing radiation regressed on intervals of temperature change. What one finds is for the long wave, there is a very clear feedback response that is negative. For the short wave, you have this S-shaped curve, which we now realize is largely a function of a very high noise-to-signal ratio. This is rather important, though, in its own right. It's saying that the long-wave feedback is unambiguous, and this has been confirmed even by people like Trenberth and others who've looked at it. Now, what this means, and this is rather important, the water vapor feedback is a long-wave feedback. You cannot, and I think I have a slide on that, yeah, probably not, you can't separate the water vapor feedback from the cloud feedback at upper levels, because the water vapor only affects the region not covered by the upper level clouds, but that's variable. So the only thing you have is the long wave feedback. Remember, the reason you got the big range in sensitivity was you had 0.5 for the water vapor feedback. This is saying that even if it existed, it is canceled and exceeded by the cloud feedback or something else. So now when you come to that 1 over 1 minus f, you don't have the 0.5 to start with. You have 0. To get it to go from 2 to 5, you needed to have 0.3 for the positive feedback. But if you start with 0, 0.3 does nothing. You're in the flat range of that curve, so you're insensitive. So this already, if it's true, is telling you you're not sensitive. Okay. This is just saying that. What about extreme weather? I'll just do that briefly. But this is one of the crazier things. Extreme weather is pure propaganda. The IPCC itself acknowledges no relation. That's important to understand. They have said that. I keep insisting, when you're attacking the IPCC, it's all well and good, but check what's inside it. What's inside it is often something that would argue against the hysteria. And given that it's in the IPCC, you can use it to your advantage. In the extratropics, outside the tropics, what forces weather disturbances and variance is the difference in temperature between the equator and pole. All models of warming say that goes down, not up, in a warmer world, which would suggest you have less potential for storms and less variance. It doesn't matter that that's the case. It's not scary, so you say the opposite. You also have to have a perspective. This is March 12, 2013. Doesn't matter, I could pick any month. This is in the Boston Globe, our local newspaper. Every day it shows you the high and low temperature, the dark blue, for the preceding 30 days or so. It also shows the average high and low, that's the gray in here. And it also shows you the difference between the record-breaking high and the record-breaking low for each day, although those often occur many years ago. There is also a line here, a red line. And what that red line is simply the width of that line is the total range of global mean temperature anomaly for the last 150 years. Keep that in perspective when you discuss climate change in terms of that variable. The variance, and I've given this to high school students, it's kind of funny. The paper also publishes a map of the temperature for North America for the day. And the exercise I ask the students to do is to estimate from this map what the record-breaking high and low was for the day, no matter what year it came from. And they always get it within a few degrees. It's the highest and lowest temperature on this map. One is advecting air from someplace else. It's not coming from changes in the radiation.